Oh, hello there. Doesn't that calzone look yummy? I bet it sure does taste good. When you slice into a calzone, you get all that good stuff that kind of spills out. Don't you ever just wonder, how much stuff can you actually fit in calzone? So today we're going to use calculus and figure this out. We're going to model this and then create, using an integral process, find the actual volume of that weird shape. Now I look at that, and if we rotate, we smush it around, kind of exaggerate it a little bit, I think that calzone looks an awful lot like the curve y equals 2 sine x. I mean, look at it. Look at it down there. That's definitely a calzone. Yep. Everything works out. So how can we find the volume of that shape? What I think about here is it's kind of a half circle along the way. And if we take our calzone, the outline of the base, we've got a bunch of half circles stacked on top of there. So really what we want to be able to do is put all of that bits together. And we can very easily find the area of a half circle. Well, area of a circle, half a circle is going to be pi r squared over 2. Well, there's our radius. At some value x then, since we've got that whole distance all the way across, is really the y value, then at some value for x, our radius is really going to be half the distance of that y, half of 2 sine x. So really, the radius is then sine x. And if we want the area, area, we're not looking for area, we're looking for volume. If we want like the area of one of those circles, it would be pi over 2 r squared, so pi over 2 sine squared. That's just one slice. We want this slice also. We want this slice. We want every single slice in between. That's where our calculus comes into play. Rather than thinking about like, okay, we've got to find all of these little slices. Well, let's give this a little bit of thickness, some three-dimensionality. So we've got like this slice here, and we can find just that slice, the volume, because it'd be, well, the half circle times the thickness of that slice. Well, that thickness, is actually some dx, or rather thinness. We can make that infinitely thin. And so the volume of one slice, one of these, I'm going to say cross-sectional slices, because if we look straight down on it and take our knife and slice right through, we've got this circle, or half circle, infinitely thin. So the volume of one thin slice is going to be the area of that base, pi over 2 sine squared, multiplied by the thickness, dx. Well, how many thin slices can we make? That's where the infinite number comes in. And this looks an awful lot. We want to add together all of those slices. Let's find that volume. Well, volume 1, just to say it one more time, is pi over 2 sine squared x dx for that thickness. And we want all of them. Now, calculus, for adding all of those together, that's the integral. So here, we've got an expression that's going to give us the volume of all those slices. Now I'm going to set some bounds on here. I'm going to go from 0 to pi over, just to pi. And I'm basing that off of that horizontal region of the graph, y equals 2 sine x. So we're able to create an integral equation that is going to give us the volume. We take one slice, in this case it's a half circle, and we're going to add together an infinite number of infinitely thin circles. Now I'm going to do a little bit of manipulation here to evaluate this integral. I'm going to take advantage of one of my trig identities, that sine squared is actually 1/2, 1 minus cosine 2x. And that's based off of one of the cosine double angle identities. So I'm going to make this substitution. That volume is now pi over 2 times 1/2. We're going to go from 0 to pi of 1 minus cosine 2x dx. And I've got an integral that I can evaluate. Volume is pi over 4. Taking the antiderivative of this, we have x subtract 1/2 sine of 2x. I'll leave that to you to verify that. I'll evaluate it from 0 to pi. Just making our substitutions using our integral evaluation theorem, we're going to get volume is pi over 4 multiplied by, well, that's going to be pi. When you substitute in pi, subtract 0, we've got pi squared over 4 cubic units of goodness inside our calzone. Doesn't that look yummy? All right, I'm going to do one more example of finding the volume using these cross-sectional areas. The big idea is that we're going to take a slice through some object. If we can find the area of the face of one slice, then we've given it some thickness, some dx. The big idea here is that our volume is going to be the integral of the area of one of those slices, dx. Just like going back to volume of a box, base times width times height. Volume of a cylinder, pi r squared times height. Just now, that base is changing in some means because it's defined on some curve. I'm going to do one more example. I'm going to go to letter B on the next page of your notes, if you're following along with my notes. So we're going to find, we've got this circle. We've got x squared plus y squared equals 1. And we're going to stack squares on top of this. So that we've got, if we're taking a solid and slicing through, we're going to have all of these square cross sections. So I'm thinking, okay, volume is going to be the integral of the area dx. Oh, area of a square is the base squared, side squared. The base is that whole distance across there. There's our s. Now I'm going to take my equation here, x squared plus y squared equals 1. I'm going to solve this for y equals square root of 1 minus x squared. That's the distance from our x-axis up to the edge of that circle. So we have y equals square root of 1 minus x squared going forward and going the other direction. So the entire side s is actually 2 square root 1 minus x squared. No matter where we are, for any value of x, the base of that circle, base of the square, fitting inside that circle is given by 2 square root of 1 minus x squared. So the area of one face, when we slice through and we see that square, is going to be 2 square root 1 minus x squared, quantity squared, or the area of one face is going to be 4 1 minus x squared. Now that's one specific cross-sectional area. That's one slice, just the face. We're going to give it a little thickness there. Give it that thickness. That's where calculus comes in. Our thickness is going to be dx. That's just a rectangular prism. Base times height times width. So our volume is going to be the integral. Now I'm going to substitute in my equation, my expression for the area. I've got a constant of 4. I'll take that out. We have 1 minus x squared dx. Our bounds are going to go from -1 to 1 because those are the horizontal bounds on our circle. Let's go back then. Our volume is going to be given by 4. I can evaluate the integral. That's going to be x minus 1/3 x cubed evaluated from -1 to 1. I'll leave it to you to make that substitution. We're going to get 4 multiplied by 4/3. And so we've got a volume of 16/3 cubic units. Try it out. See you later.